Imagine a scorching summer stretching on for weeks, almost causing a drought, and you begin to long for a rainfall so the weather can finally cool down. And then, when the sky darkens and the first raindrops begin to fall, you feel a surge of joy. But then 1 week, 1 month, and then 1 year pass, and the rain still does not stop. Now try to push your imagination even further. Not 1 week, not 1 year, but 1,000 years, then 1 million years, and finally nearly 2 million years of unceasing rain. Can you imagine how chaotic the world would become? In reality, this event did occur around 234 million years ago, and scientists call it the Carnian Pluvial Event. It caused a mass extinction that is often forgotten, and more importantly, it paved the way for a group of creatures that we all know and love: dinosaurs. In this video, we will explore together the astonishing story of a rainstorm that lasted nearly 2 million years, how it destroyed the old world, and why. From within that catastrophe, an entirely new era of life was born. Before the Carnian rains began, Earth was a planet that looked completely different from the lush, humid world we are familiar with today. If you could stand on Earth's surface more than 234 million years ago, you would not see dense forests or long, winding rivers. Instead, you would face a dry, harsh world that felt more about survival than abundance. This was the middle of the Triassic period, a time when life was still recovering from the greatest mass extinction in history, an event that wiped out more than 90% of all life on Earth. At that time, all of today's continents were still joined together, forming a single enormous supercontinent. The clustering of land masses into one giant block made the global climate extremely extreme. Regions deep within the continent received almost no moisture from the oceans, leading to prolonged aridity. Daytime temperatures could soar very high, while nighttime temperatures dropped sharply, creating brutal contrasts that only a few organisms could endure. Water, the fundamental element of life, became a precious resource. Rivers and lakes were sparse, and many regions had almost no stable surface water. Rain was not a regular occurrence, but a rarity. As a result, terrestrial plant life took on the appearance of a drought-stricken world. Low-growing plants with tough stems, small leaves, or needle-like foliage to reduce water loss. Dense forests were almost non-existent. Instead, open landscapes dominated, covered with sparse shrubs and impoverished vegetation. In this context, wildfires became a familiar part of the ecosystem. Dry vegetation ignited easily, and just a single lightning strike from one of the rare storms could burn vast areas. Ironically, fire itself helped maintain the fragile balance of this world. Many plant species evolved to withstand or even exploit wildfires as a means of regeneration. Life persisted, but it was a life stretched taut against nature, where every organism had to adapt to the extreme in order to avoid extinction. Ancient reptiles played the dominant role, their bodies well adapted to hot and dry conditions. They possessed skin that limited water loss, and more effective thermoregulation than many other early animal groups. Alongside them were therapsids, the distant ancestors of mammals, struggling to carve out a place in a world that was anything but forgiving. The competition for survival was quiet yet relentless, as food resources were limited and habitats unstable. In this arid world, dinosaurs had already appeared, but almost no one noticed them. The earliest dinosaurs were small, slender, and rare, occupying only very modest roles within the ecosystem. They were neither apex predators nor overwhelmingly abundant, faced with rivals better adapted to hot, dry conditions. Dinosaurs seemed like creatures that had arrived ahead of their time. The first true dinosaurs shared one trait that made them easy to underestimate: their small size. Compared with modern imaginations of dinosaurs as gigantic biological machines, these early inhabitants were only slightly larger than today's medium-sized predatory mammals. They walked on 2 hind legs with light, agile bodies suited for rapid movement across open, arid landscapes. Yet this very smallness made it difficult for them to compete directly with the true rulers of the age. One of the most representative examples is Styracosaurus. Although it is often mentioned as one of the largest dinosaurs of its time, it measured just over 2 meters in length and weighed roughly the same as a medium-sized dog. In the Triassic world, that was not a size that conferred absolute advantage. Styracosaurus was a predator, but its prey consisted only of smaller animals such as cynodonts, rhynchosaurs, and other synapsids. It did not sit at the top of the food chain, but rather occupied a middle position, hunting while constantly remaining alert to larger predators. Alongside it was Burrialestes, an even smaller species. With sharp teeth and pointed claws, it initially appears to be a nimble predator. However, what makes Burrialestes special lies not in its size or its diet at the time, but in its evolutionary position. Despite its carnivore-like appearance, Burrialestes belongs to the sauropodomorph lineage, a group that would later give rise to the gigantic long-necked herbivorous dinosaurs. Scientists recognize this through subtle anatomical details, a downward curving jaw structure suggesting the ability to process plant matter, and an elongated deltopectoral crest on the upper arm bone, indicating a completely different evolutionary trajectory from that of pure predators. At this point, the future of dinosaurs was still hidden within seemingly minor morphological traits. Beyond the creatures considered true dinosaurs, the Triassic world was filled with their close relatives, a group paleontologists often refer to as dinosauromorphs. These were animals that almost became dinosaurs, sharing many anatomical features but lacking the full set needed to be classified as true dinosaurs. Names such as Lagosuchus, Marasuchus, and Saltopus represent a very common form of life at the time. Small bodies, long hind legs, fast bipedal running, and an appearance like strange lizards from another world. They were agile, well-adapted, and occupied many ecological niches that dinosaurs would later take over. It is important to emphasize that at this stage, dinosaurs were not dominant at all. They were only a very small part of the extraordinarily rich tapestry of Triassic biodiversity. On land, other archosaur groups were the true rulers. Rauisuchians, large, powerful apex predators, stood at the top of the food chain. Phytosaurs with crocodile-like bodies dominated rivers and shallow aquatic environments. Atosaurs, herbivores protected by thick armor, moved slowly but were safe from most predators. Alongside them were widespread herbivorous groups such as dicynodonts and rhynchosaurs, which were perfectly adapted to arid conditions and played crucial roles in the ecosystem. These creatures were far more numerous, successful, and stable than the young dinosaurs. In addition, this period also saw the emergence of smaller but highly promising reptile groups, such as the ancestors of modern lizards and snakes, as well as strange evolutionary branches like Shuvosaurids and Pterosauromorphs, creatures that would eventually pave the way for the rise of flying reptiles. Underwater, marine reptiles were just beginning to appear, experimenting with different body forms and lifestyles in oceans that were slowly stabilizing after the previous mass extinction. Placodonts with stocky bodies and teeth adapted for crushing shelled organisms swam near early coral reefs. Meanwhile, cephalopods such as belemnitids began their long evolutionary journey, becoming an important part of the marine food chain. While dinosaurs remained little more than obscure names among countless other organisms, in a distant place, what is now the western margin of North America, far beneath Earth's crust, a colossal geological force was quietly building. The Carnian Pluvial Event did not originate from a minor orbital change or a brief climatic fluctuation. It was triggered by a planet-scale explosion arising from Earth's own crust. The primary culprit behind this catastrophe was a series of enormous volcanic eruptions known as the Wrangellia flood basalts. This was not the kind of volcanic eruption we typically observe today, with a single volcano spewing lava for a few days or months before settling down. Wrangellia belonged to a rare and extremely dangerous type of geological event that scientists call a large igneous province. Such events do not occur over short timescales, but instead last for hundreds of thousands to millions of years. with lava erupting continuously and covering vast regions beneath layers of basalt several kilometers thick. In the case of Wrangellia, the scale of the eruptions was so immense that it is difficult to grasp by modern standards. The lava flows not only spread across the land surface, but also released enormous quantities of gas directly into the atmosphere. The first and most important consequence was the massive release of greenhouse gases. Wrangellia's volcanoes pumped carbon dioxide into the atmosphere in quantities far exceeding normal natural levels. Heat from volcanic activity and the initial warming of the oceans destabilized methane clathrates, frozen pockets of methane trapped beneath the seafloor and within sediments. As they broke down, methane was released into the atmosphere rapidly and in vast amounts. This gas is many times more potent than carbon dioxide in the short term, and its presence pushed Earth's climate system beyond a dangerous threshold. The next step in the chain reaction was global warming on an unprecedented scale for that time. Earth's average temperature surged by 4 to 8 degrees Celsius in a very short geological interval, for a planet already accustomed to the hot, dry climate of the Triassic. This increase was like turning a heater to maximum in a room that was already stifling. The ocean's warmed polar ice, if any still existed, nearly vanished, and temperature differences between regions of the planet began to shift dramatically. This warming effectively pressurized a system that had always been quietly operating, the hydrological cycle. As temperatures rose, water on Earth's surface evaporated faster and in far greater quantities than before. The oceans became enormous evaporation engines, continuously feeding water vapor into the atmosphere. Warm air can hold more moisture, making the atmosphere increasingly thick and humid. But this system could not accumulate indefinitely. When water vapor reached saturation, it had to return to the surface as rain. And because the supply of moisture never diminished, these rains were no longer localized or seasonal events. They became prolonged phenomena spreading across the globe. Rain fell more heavily, more frequently, and more violently than at any time Earth had experienced in tens of millions of years before. What made the Carnian Pluvial Event especially dangerous was not only the intensity of the rain, but its persistence. This was not merely a wet period lasting a few thousand years before ending. Wrangellia's eruptions continued over long spans of time, constantly replenishing greenhouse gases in the atmosphere and keeping the planet locked in a hot, humid state. The water cycle was driven into an inescapable loop. High temperatures caused intense evaporation. Intense evaporation produced heavy rainfall, and heavy rainfall in turn disrupted Earth's entire surface. As the Carnian Pluvial Event entered its full phase, Earth moved into a state that modern humans can scarcely imagine. A world where blue skies were rare, where water falling from above became the force that reshaped every landscape, and where ecological stability that had existed for millions of years was shattered at its very foundations. However, one important point must be clarified. The Carnian rains were not a single, uninterrupted drizzle lasting 2 million years in the literal sense. Instead, this was a period during which average global rainfall surged dramatically and persisted over long spans of time, punctuated by episodes of extremely heavy, violent rainfall that repeated far more frequently than in any earlier period. Geological evidence shows that the power of these rains went far beyond the ordinary notion of heavy rainfall. Water did not simply soak into the ground and recede. It became a relentless force of erosion. Across many regions of the supercontinent Pangaea, sedimentary layers that had accumulated over millions of years were stripped away, with successive layers of soil and rock worn down until even the bedrock was exposed. Ancient rock layers lying close to Earth's crust, normally buried beneath kilometers of soil and sediment. The exposure of bedrock is a clear sign that rainfall intensity and surface runoff reached extreme levels, powerful enough to effectively strip bare the planet's surface. Another line of evidence, less visually obvious but no less compelling, comes from the widespread presence of amber in rock layers dating to this period. Amber is fossilized tree resin, and for it to form in large quantities, very specific conditions must be met. Vigorous forest growth, high humidity, and most importantly, rainfall that far exceeds evaporation. The abundance of amber in Carnian sediments indicates that rainfall was not only heavy, but also stable and prolonged enough to sustain large-scale humid forests. Something that would have been nearly impossible in the arid world that came before. Under the constant influence of rain, the face of Pangaea began to change in profound and irreversible ways. Vegetation exploded in places where life had previously survived only at minimal levels. Tropical forests and wet ecosystems spread, turning formerly barren regions green. Swamps became increasingly common, emerging as a defining feature of Carnian landscapes. In particular, peat-forming forests, ecosystems rich in organic matter that develop under wet, low-oxygen conditions, were re-established on a vast scale. These forests not only stored enormous amounts of carbon, but also completely transformed soil structure and nutrient cycles in surrounding environments. At the same time, extensive floodplains formed along river systems that were newly created or greatly expanded by rainfall. These floodplains were repeatedly submerged and then exposed again, creating highly dynamic environments that only certain organisms could tolerate. Excess rainfall also led to the formation of enormous inland lakes. In many places, water accumulated in geological basins, creating lakes whose surface areas could rival or even surpass the Great Lakes of today. These bodies of water altered regional climates by moderating temperatures, but they also drowned older habitats, forcing terrestrial organisms to migrate or face extinction. At first glance, Earth's transition into a greener, wetter world might suggest abundance and flourishing life. But for most Triassic organisms, this transformation was a catastrophe. Species that had evolved to survive in arid environments, with water-conserving physiology and behaviors suited to hot, dry climates, were suddenly thrust into a completely unfamiliar world. Soils became waterlogged, habitats flooded, and food sources changed or vanished. Food webs that had once been stable were disrupted at their very foundations. On land, the most obvious victims were plants and animals adapted to the dry conditions of the earlier Triassic. Large herbivores that depended on drought-tolerant vegetation were hit first. As rainfall intensified, soils became saturated and older plant communities collapsed, and their food sources disappeared within a geologically brief interval. Groups such as Dicynodonts and Rhynchosaurs, once widespread and successful across multiple continents, began to decline rapidly. They lost not only their food, but also their suitable habitats, as dry landscapes were replaced by swamps and humid forests. Even organisms that seemed more water-tolerant, such as phytosaurs, animals resembling ancient crocodiles, were not entirely safe. Although they lived near water, they still depended on the stability of river and coastal ecosystems. Excessive rainfall altered river flow, caused frequent flooding, and destroyed breeding grounds. This constant instability led to declining phytosaur populations, and many lineages of the group never recovered. In the oceans, the effects of the Carnian rains were less immediately visible, but no less devastating. Enormous volumes of freshwater runoff carried sediments and nutrients from land into the seas, drastically altering the chemistry of shallow marine environments. Salinity dropped abruptly, while nutrient enrichment triggered eutrophication, causing massive blooms of algae and microorganisms. When these organisms died, they consumed large amounts of dissolved oxygen, creating oxygen-poor waters, conditions nearly uninhabitable for many marine animals. Early coral reefs, highly sensitive to environmental change, suffered severe losses. Fluctuations in salinity, temperature, and oxygen caused many reef ecosystems to collapse. Species that depended on reefs for shelter and food vanished along with them. Some groups of marine invertebrates, which had flourished after the previous mass extinction, were once again pushed to the brink. Even newly emerging marine reptiles such as placodont's were not spared. Despite their adaptations to marine life, they still relied on stable, food-rich coastal environments. Prolonged disruption prevented many species from maintaining populations large enough for long-term survival. The clearest and most immediate beneficiaries of the rain were plants. as rainfall increased sharply and remained stable over long periods. The greatest constraint on Triassic vegetation, water scarcity, nearly disappeared. Soils became moist and increasingly nutrient-rich as sediments were continually transported, creating ideal conditions for plant expansion. Plant groups such as ferns exploded in abundance, rapidly colonizing low-lying areas and swamps. Conifers, with their flexible adaptations and structures that allowed them to thrive under diverse conditions, began to diversify rapidly and gradually became dominant components of forests throughout much of the Mesozoic. Alongside them, the bonnetatales, a group of ancient plants with distinctive forms, also expanded quickly, enriching the structural complexity of terrestrial ecosystems. This botanical explosion did more than reshape landscapes. It created an entirely new biological foundation. A surge in biomass meant more abundant and stable food supplies for herbivores, triggering expansion across entire food webs. For dinosaurs, the Carnian Pluvial Event was not an instant explosion but an essential turning point. With their agile bipedal posture, efficient locomotion, and high adaptability, dinosaurs rapidly filled newly opened ecological niches. Their rate of diversification skyrocketed, not only in species numbers but also in body size and ecological roles. From small-bodied animals, they began branching into many forms, experimenting with new lifestyles in the humid post-Carnian world. A striking illustration of this rise is found in the Ishigualasto Formation of Argentina, which preserves one of the clearest snapshots of life immediately after the Carnian Pluvial Event. In rock layers dating to just after the event, scientists have discovered fossils of at least 8 different dinosaur species, reflecting astonishing diversity over a short geological span. Names such as Eoraptor and Eodromius represent small, agile dinosaurs, while Antias, Panphagia, and Sanjuansaurus reveal diversity in diet and form. Most prominent is Herrerasaurus, one of the largest carnivorous dinosaurs of the Triassic, reaching lengths of about 6 meters. Not long after this phase, the first signs of dinosaur gigantism began to appear. Only after the Carnian Pluvial Event did the first truly gigantic dinosaurs emerge. Lesomsaurus, an early sauropod measuring around 12 meters in length, stands as clear evidence of this trend. The appearance of such massive bodies indicates that the new environment had become stable and resource-rich enough to support creatures with enormous energy demands. However, it is important to emphasize that the Triassic had not yet fully become the age of dinosaurs. The post-Carnian world was an open playing field, and dinosaurs were not the only ones to seize the opportunity. Many other archosaur groups also flourished, and some continued to dominate specific environments. Etosaurs are a prime example. These four-legged, heavily armored herbivores benefited greatly from the explosion of new vegetation. They specialized in feeding on conifers and ferns, while former competitors such as rhynchosaurs failed to adapt to these new food sources. As a result, Etosaurs became one of the most successful herbivorous groups of the late Triassic. Phytosaurs, semi-aquatic predators, also entered a golden age. The expansion of swamps, rivers, and enormous inland lakes turned the post-Carnian world into an ideal environment for them. They diversified rapidly, grew larger, and became dominant predators in freshwater ecosystems. For any organism living near water at the time, this new world was truly a nightmare, a place where ambush predators could strike from anywhere. Even Rhoesuchians, the apex predators on land, were not entirely eliminated by the Carnian rains. On the contrary, many new genera of this group appeared during or immediately after the prolonged rainy phase. Their body sizes increased, perhaps to keep pace with increasingly large prey in the new ecosystems. Giants such as Saurosuchus, reaching lengths of up to 7 meters, reveal an evolutionary arms race in which predators and prey continually upgraded to avoid falling behind. Meanwhile, evolutionary lineages leading to modern turtles and crocodiles also made important advances. Early turtle ancestors began experimenting with protective shell structures, while crocodilomorphs, early relatives of crocodiles, diversified in form and lifestyle. These changes laid the groundwork for the long-term survival of these groups, extending all the way to the present day. Finally, after nearly 2 million years, the Rangelia volcanoes ceased erupting. Greenhouse gas levels in the atmosphere gradually declined. Rainfall became less frequent, and the hot, dry climate characteristic of the Triassic returned. Although the climate appeared to have returned to normal, the effects of the Carnian Pluvial Event were permanent and profound. The world had changed. This forgotten mass extinction wiped out many formerly dominant groups, clearing the way for new winners. The changes experienced by animal lineages shaped their evolutionary paths, directly setting the stage for the Jurassic period and the full dominance of dinosaurs. So the next time it rains, remember that a downpour from 234 million years ago may be the very reason we have turtles and crocodiles today. If you find the story of a rainstorm lasting 2 million years and the birth of a new world intriguing, don't forget to hit like to support the video and subscribe to the channel so we can continue exploring other astonishing mysteries in Earth's history and the story of life. The greatest stories of this planet are still waiting to be told.